Now, if we want a more quantitative look, we're going to use the Nernst equation. And so the Nernst equation, again, is used for cells that are not in standard state. And this is the basic form of the Nernst equation. There's another form that you'll see where you have, let's see, I'm going to derive it, I think, on the next slide. So this is the standard form that you use it in most frequently. Oops. Let me put all these up here. Uh-oh. I'll have to fill in some things here. Okay, so we're starting with, from the previous chapter, this relationship between delta G, when it's not at standard state, and the delta G at standard state. So we're going to start with this equation, okay? We're going to substitute in the relationship that delta G naught is minus NFE naught, and that delta G is going to be minus NFE. Okay, and we put that in there, we get, this slide has gotten messed up for some reason. This is E equals E naught minus RT over NF natural log of Q. So this is one form of the Nernst equation. Okay. R is the 8.3145 value. Temperature is in Kelvin. N is still number of electrons transferred. F is the Faraday constant. Okay. Q is our reaction quotient. All right. If you're at 25 degrees Celsius, then you can use this form of the equation, and that takes into account 25 degrees Celsius and the conversion between the natural log and the base 10 log on that form. Alright, so let's take a look at how we might use this. If we have a voltaic cell based on that reaction there, and so we want to know what must the iron be to increase E cell by 0.25 above E naught. Alright, so what do we have going on here? Oops. Go back. We need to see what our E naught is going to be. So the iron is being oxidized. So iron 2 plus 2 electrons. Okay, the reduction is minus 0.44, so my oxidation is going to be plus, and my reduction is going to be for copper 2 plus to copper is 0.34. So E naught is going to be 0.78. Okay, so we want, alright, let's just do this generically first. E is 0.78 volts minus 0.0592 over, our N is going to be 2, log of, and our Q here is going to be Fe2 plus over Cu2 plus. Products over reactants. Okay? So it wants to know, we want it to be, to increase it by 0.25. So our new E cell 0.78 plus 0.25 is going to be 1.03 is 0.78 volts minus 0.0592 over 2. Log of the iron concentration is what I want to know, and the copper is 0.3 molar. Okay, so let's see. 1.03 So that's going to be 0.25 equals minus 592 divided by 2. 296 log. Okay, and so 0.25 divided by negative 0.0296. So I get minus 8.45. And so 10 to the minus 8.45 is going to equal V plus 2 over 0.3. So that is right. Just double checking. So I'm getting, let's see, that and then times, let's see, that gives me 3. I'm going to move that over here. 3.55 times 10 to the minus 9 equals Fe plus 2 over 0.3, okay, times 0.3. So that gives me that the iron needs to be 1.06 times 10 to the minus 9th. Okay, and that, okay, I guess that does make sense, because if you think about it, that's a pretty big increase in the cell potential. And so in order to increase the cell potential, I need to not only, if I increase the copper, just think of it from Le Chatelier, if I increase that copper, that's going to shift it right, but then to shift it even more to the right, I've got to decrease the iron. So we would expect the iron to be lower than 1 molar, the standard condition, and for such a, that's a relatively large increase, and so I guess that's why the iron concentration is dropping so low there. Okay, now here we've got an application of the Nernst to a concentration cell. So here not only are we going to think about it from the standpoint of Le Chatelier, but we're also able to get some quantitative values in here of the actual potential of this cell. So let's look here and see what we get. If we apply this, we have that, if you remember, our dilute cell is going to be the anode. We're going to have oxidation of the dilute going to the, let's just do it this way. Ag plus dilute is going to get, no, sorry, that's Ag. Dilute is going to Ag plus dilute plus an electron. So oxidation is occurring there, and then in the concentrated cell, the Ag plus concentrated, that's going to get reduced into the silver metal. And so if we put these two together, okay, our concentrated, the product is going to be the dilute silver ions. The reactant is going to be the concentrated silver ions. So that's how we get this as our value for our reaction quotient for the concentration cell. Okay, so you get your dilute over your concentrated, because that's what's going to happen every time. The dilute is going to be oxidized, and the concentrated is going to be reduced, as long as we're talking about the cations in here. So what do we have for E naught if it's a concentration cell? Well, the E naught is based on the reduction and oxidation potentials. And here, since we are reducing and oxidizing the same thing, my E naught is going to be 0. Okay, for this reaction, my N is going to be 1 for the silver, and log of, and here it says our dilute is 4 times 10 to the minus 4th, and our concentrated is 0.01. Okay, so we're going to get 0.0592 times log of 4. Okay. And I get an E cell of 0.0828 volts. Okay, you can calculate equilibrium constants of redox reactions. Basically, what you want to keep in mind is that as they proceed, the concentrations of products increase, reactants decrease, and then when they reach equilibrium, Q is going to be equal to K, and at equilibrium, E cell will be 0. So use these two facts here, plug them into the Nernst, and you get this modified version there, where we can now solve for the equilibrium constant. And here's just another rearrangement of that. And again, the thing to remember, that's why I put it there, is that the use with this value here is when it occurs at 25 degrees Celsius. Okay, electrolysis. This is basically the opposite of a galvanic cell. Here we are taking a non-spontaneous reaction and putting energy into the cell to cause it basically to flow in the non-spontaneous direction. This is commonly used in electroplating, for example. Here's where we have the same set of half cells. Here's our zinc and copper, and if we let the electrons flow in the spontaneous direction, then we would be oxidizing the zinc and reducing the copper, and we would be producing a voltage of 110 volts. Here, in order to cause it to go in the opposite direction, in other words, in order to reduce the zinc and oxidize the copper, all I need to do is to apply a voltage greater than 1.1 volts, and I can make this reaction go in the opposite direction. Electrolysis, here's a good example here of where we are taking a molten salt and we are reducing the cation and oxidizing the anion. Okay, electrolysis problems are pretty simple to solve. They're just like a big factor label problem. Usually we'll have current and time, and those you can relate those two variables by this relationship, that 1 amp of current is 1 coulomb per second. From that you can get a quantity of charge, and once you have the quantity of charge, that relates to the number of moles of electron using Faraday's constant. That N is the number of moles of electrons. And once we have the moles of electrons, we can translate that into moles of the reacting species. And then using its molar mass, we can connect that to the grams of the analyte. And you can do these in this direction, starting with current and time, or you can start with grams of analyte, but these are the conversion factors that you would use. So let's look at an example. Okay. This is kind of a step-by-step here. But basically what you'll see is we're going to use a factor label to do this. So if I have 5 amps of current, I want time, and I want to produce 15.5 grams of silver from Silver Plus. So here, let's see, if I have 15.5 grams of silver, and the molar mass of silver, I had a periodic table here. Molar mass of silver is, we'll just do a rough 108 grams in 1 mole of silver. And then for every 1 mole of silver, I need 1 mole of electrons. And 1 mole of electrons is 96,485 coulombs. Okay, so that would give me coulombs. Let's just stop there for a minute. That gives you 15.5 divided by 108 times 96,485. So I need 1,308 or 13,847 coulombs of charge that need to pass. And if I have a current of 5 amps, so that's 5 coulombs per second. I guess I could have kept going with that. I would have had room, but 5 coulombs in 1 second, and that's going to give me that it would take 2,769 seconds to produce that much silver from silver ions. And most of these electrolysis problems are exactly like that. Like I said, you'll either be starting with the mass that you need, like we did in this one, or you'll be starting with an amp and a time, and then they're asking you, well, how much or what mass can you get from that? So either way, you're going to use the same types of conversions.